Check that out. Embedded. So today we're going to talk about this, and I'm going to throw a lot of jargons at you. But first, let me just put it over here. Approved by open source. Let's talk about embedded. But one thing, you're gonna listen a lot of these noises today. My house is under construction, so apologies for that. Let's start. So if you are new onto this channel and doesn't know much about me, like what I do outside this YouTube live, then let me tell you that I have a full-time job. I'm working as an embedded software engineer for almost like 2.5 years now. So I'm making this video to share with you all different skills you require to make a career in embedded systems, specifically in Indian industry. This video has been requested by a lot of my different friends, especially who are in undergraduate or who are in school. They keep asking me what path they should take to build a career in embedded system. A lot of them are very passionate about embedded systems and hardware in general, and they keep asking me like what skill sets are required to make a career in this domain. So I will share every detail in this video, so keep watching and let's get started. So one thing that I wanted to mention in the very beginning of this video, embedded system domain is not just only for electronic students. It's a myth in India specifically, where only electronic students think that they can move into a embedded system. But in reality, as I have seen in the industries, a lot of different computer science students, electrical students, and even mechanical students are in embedded system domain, because it's a very vast domain and a lot of different things are available for each and everything. So don't have a branch specific mindset. Irrespective of any engineering branch you are in, you can still make a career in embedded system and have a good earning pay scale. So that was a small disclaimer I wanted to do in the starting of this video. A little background about me: I started working on the embedded system during first year of my engineering. I attended a robotics club workshop in which they taught how to program microcontroller, how to run motors, and how to sense environment variables using different sensors. And from there, I kept working on for the next 3 years of my engineering, and ultimately I do internships in embedded domain for different companies, some for 2 months, some for 6 months, and now I have a full-time job in embedded system domain, and really liking it because I'm very passionate about this. I enjoy working with hardware, and I enjoy programming silicon directly, controlling sensors, and porting operating system on them, and lots of different things are there. I also make a lot of different hobby projects from embedded system, either to automate my house or about my drones thing. These are also very good example of embedded system. So yeah, that was a small background about me. Why to make career in embedded system? Maybe because you are very passionate about it, maybe because you like tweaking with hardware, or maybe you just wanted to have a good pay scale, because embedded engineers are highly paid. Either they are firmware engineers or hardware engineers, or even the core software engineers who also build middleware and applications on top of it, specifically for embedded domain. They have a pretty good salary. And even if you are thinking to start your own company, maybe it's a hardware based, then also you need to have skills for embedded domains, and that's where these skills comes very handy. So like just look around you. You will see air conditioner, it's an example of embedded system. You see television, it's an example of embedded system. You see your smart watches, your smart band, everything is embedded system. Even your mobile phone, it's running an operating system. It is having a microprocessor inside it, an ARM base. So everything is a embedded system. And recently, Internet of Things, that is IoT, has impacted all the different industries, and the demand for embedded engineers are everly growing since then. So without wasting any time, let's discuss about the skills required. So I personally broadly classify embedded system engineers into two categories, that is the hardware engineer and the software engineer. So these are the two major aspects of embedded system, because the embedded product is a combination of a hardware, that is your SoC or silicon on chip. Then you also put a firmware on it, or maybe an operating system on it, and then their software engineers comes into picture. So it's a combination of hardware and software, and special company do require specialized hardware and software engineers to do their work. And you can make career in a hardware domain or pure software domain depending on your interest. So let's quickly talk about embedded hardware domain. Personally, I don't have very in-depth knowledge of embedded hardware domain, because I do mostly embedded software part. But again, I can tell you that embedded hardware engineers do different things, like making schematics for a product, making PCB designs, and making power supply designs. So again, talking about power supply, it's again a huge domain. People make whole career out of it. Buck converter, boost converter, step-up converters, step-down converters, AC to DC converters, ripple factor, a lot of different jargons I'm going to throw you. If you're not getting this, then pause this video and Google it out. That will help you more. I am not an embedded hardware engineer. I'm not expert in that domain, but I know people who do this kind of things. So maybe if you want to know more, just comment it down below, and maybe I can bring someone into this channel who can talk more about this. So again, summarizing, embedded hardware engineer basically does schematic layout, embedded board design or PCB designing, power supply design, a lot of different analog things are here. So if you are going into schematic and PCB designing, then you need to know a couple of softwares like OrCAD is there, Eagle is there. These are the industry standards which you need to know. I will be focusing more on embedded software domain because that is what I do, that is what my job is all about. So now let's talk about embedded software engineers and what they do. So it's a huge domain and people make careers in different parts of this embedded software region. But if you are a student like what I'm assuming, then here are the steps which I would recommend you to follow to make a career by the end of your 4 years of graduation. You would be having enough skills to be applying for embedded software domains. So my very first recommendation for budding embedded software engineers is to learn C programming language, and as an embedded software engineer you would be working 95% on C programming language, so it's a good idea to learn it sooner than later. And as an embedded software engineer you are expected to be good at it. Either you are working on bootloaders, you are working on middleware, or you are working on kernel. C is everywhere and you cannot escape it. So my recommendation is to take a course like CS50 on edX, or take a book and read it like Dennis Ritchie, and you can code C programs on a computer and see how everything works, and go as deep as possible, like basic C, then system programming, then kernel programming, then device drivers. You can do everything by reading books or online courses. And simultaneously you can learn microcontroller, which we'll be talking about in a bit. So now by the time you have better understanding for C, now it's time to pick up the hardware and do actual embedded software programming. And before doing anything big rocket science in embedded domain, I would recommend to go and buy a microcontroller known as Arduino. And it is a very famous microcontroller. You can get a clone version of it for like 400 to 500 rupees Indian. And this microcontroller will be the gateways to your embedded system, and this will also tell you that if you have interest in this domain, and without wasting any much money, you can either exit it out or choose some other domains as your career, like electronic design automation or VLSI. But if you will have good experience with this microcontroller, then you can continue forward and make career in embedded systems. So buy Arduino, 400-500 rupees clone, around 1500 rupees for original. It's an open source hardware, and learn to program this microcontroller board. So this board Arduino can be programmed in a wiring language which is a C++ based, but if you already learn C, then you won't be having any issues. And there are tons and tons of different tutorials online on their website, arduino.cc, or different courses. I will link some of them down below for your reference. So buy this and buy a couple of sensors like light sensor, sound sensor, and whatever you can pick possible, like LEDs or buzzers, and try to interface them using the Arduino programming language or the wiring. Do not do anything on C on this. They have their own programming environment, they have their own IDE, and I would recommend to stick to that and use that. So doing small experiment with this microcontroller will really tell you that are you compatible with this field, are you enjoying what you are doing, and you really want to stick to embedded domain, or either you want to switch it out to some different careers like VLSI or application engineer. So yes, buy an Arduino, buy a couple of different sensors. I will link it down some kits below for your reference, and do some experiments with it. And once you really enjoy it, once you are sure that this is something you want to do for rest of your life, then yes, you are welcome to watch this video ahead. So now once you have exploited Arduino to its full potential, you are sure that you want to stick in this domain, you are passionate about it, you are wanted to level up, now is the time you go ahead. So by going ahead, what I mean is Arduino is good for hobby projects and learning purposes, but no company would be using it in their production environment. So that is where you want to level up, and that is where you need to learn core embedded programming, and things are not very different. And what I mean by that is, like, you can use the Arduino microcontroller, that is at Mega 328 in production, but you don't want to use the Arduino programming language because that is not something real time, that is not meant for production. Now let's talk about the high level things and what different skills you need to add to your CV to be an embedded software engineer by the time you graduate. So you already learned the Arduino, now it's time to use C programming language to control this microcontroller. So talking about the microcontrollers, there are tons of different microcontrollers available in the market based on different architectures, based on different word sizes, different memory, different IO pins and whatnot. So what would be the next level for you, and what microcontroller or microprocessor you should choose? I would highly recommend to you to take a step back and learn assembly language. So by this time you already know C programming language, you have already tried with Arduino, which is a C++ based programming language, but without a good knowledge of assembly language, you can never optimize your embedded code to such a level which company would be demanding. So it's highly recommended to learn some assembly language. You need to have some idea of different registers and what different architectures are doing with their registers, and that is where assembly comes into picture. And assembly language really gives you a full control to the memory, if I would say. You can code directly to the registers, you can put value directly to the RAM and whatnot. So having a knowledge of assembly language is really good, and I recommend to choose an x86 based microcontroller because it's a more common for assembly programming. And in colleges, in universities, there are courses for 8085 microprocessor and 8051 microcontroller. So if you have these courses in your university, do opt them. They teach in assembly language, and these are Intel based microprocessors and microcontrollers, and you can program them in assembly language and learn how different registers are working, how many registers this microprocessor or microcontroller is having, how accumulator works in x86, what is a program counter, what is stack pointer, how stack is working, what is the push and pop operation, how value moves from one register to another, what is left shifting, what is right shifting, how addition works, how subtraction works, how multiplication works. And assembly will really give you a control to the memory, and that is where you become a good embedded programmer. So good embedded programmer need to have a good control to the memory and IO ports, and assembly gives you that control. And a really good thing about assembly programming is your source code would be small and will run very fast. So that is a good thing about learning assembly. And it's not mandatory that you should know assembly, but again, if you know assembly, then you can really optimize your code. You would really have good control in everything. And in future, if there is any task to optimize your code to reduce the memory size, then you can use assembly language. You can also use assembly in conjunction with C. So yes, if you're really serious about making career in embedded domain, do learn assembly language and don't skip it. So now talking about microcontrollers or microprocessor, let's organize them based on their word size. So you will find 8-bit microcontroller, you will find 16-bit microcontroller, you will find 32-bit microcontroller, and nowadays 64-bit if you are more familiar with the microprocessor inside your phones or laptops. So these are different CPU classification based on their word sizes, and as an embedded software engineer, it's a good skill to know about each word sizes and how they work differently. So we will talk about programming 8-bit microcontroller first, and clearly two choices are available in the market. One is PIC microcontroller, full form is Peripheral Interface Controller, and other is the AVR microcontroller. There is no full form of AVR, but some people used to say Advanced Virtual RISC or Anton von RISC, which is initials of this creator. So PIC microcontrollers are made by a company called Microchip, and AVR microcontrollers are made by a company called Atmel, which is now also a part of Microchip. So these are the two common choices for 8-bit microcontrollers. PIC are mostly used in industrial applications like automations, servo controllers in industry. This is where PIC are generally used, and AVR are generally used in robotics because of their high switching speed. So you can use AVR in robotics, and these are the preferred choices. So you can either choose PIC or AVR. When I was learning, I chose AVR microcontroller because Arduino also has this AVR based microcontroller. So if you already have Arduino, you can use it and learn AVR. You do not need to buy another kit for AVR controller because Arduino Uno specifically is based on AVR architecture. The microcontroller Atmega 328 is AVR architecture based 8-bit microcontroller. So you can use this one to learn AVR. So when you learn AVR, what I mean is you learn cross compiling. So what is cross compiling is, AVR is an 8-bit architecture. You are writing your code on your PC, which is generally a 32-bit or 64-bit Intel architecture, which is x86. You want to code for AVR, you are programming on your laptop, which is x86. Then you need to cross-compile your code for this architecture, and that is what I wanted you to learn. So learn how toolchain works. So I'm throwing jargons at you again and again. If you do not understand what I meant, just Google these keywords out and you will find it out. Otherwise, you can comment it down below, and I am happy to help. So what a toolchain is basically a cross compiler, a linker, a loader, everything required to program different architectures on different PCs. So you can download the AVR toolchain. So there is a software known as Atmel Studio. Basically, it's available for Windows. You can download the Atmel Studio. I will leave some links down below. And with the Atmel Studio, you can program the AVR architecture in C programming language. So AVR architecture provided a free open source toolchain known as AVR GCC. You can download it and you can write code for it. Download the datasheet of this microcontroller or whatever microcontroller you are using. See what different registers are it's having and how you can access the register using C programming language, and try to interface different sensor with it. Try to interface different actuators with it. start with LED blinking, then move to sensor programming. Then also you can learn different communication protocols like I2C, SPI, UART. Again, I'm throwing jargons at you, but feel free to ask in the comment section what they are and how you can learn them. So I will also link it down some tutorials of AVR microcontroller, and then you can program AVR using C programming language, and there you will see how left shift and right shift operations are working, because AVR architecture or any architecture for sake, you cannot program 1 bit at a time. You have to program at least 8 bit at a time, and AVR is an 8-bit microcontroller, so you have to program the entire 8-bit registers without disturbing the other bits, and that is where your logical AND operations, your OR operations, and left shifting, right shifting comes in. And it's a good skill to learn. So this is my recommendation, to go for AVR architecture or PIC architecture in 8-bit and learn it and program it. And by doing so, you would be also learning cross-compiling, linking, and how to flash the code on this. So that is one more thing. When you compile the code, you get the binaries, you need to flash onto this. You may need to have a programmer and different things. So learn 8-bit microcontroller. My choice was AVR back when I was in undergrad, but you can choose AVR or PIC. Choose one or choose both depending on how much time or bandwidth you are having. So by this time you know how to program 8-bit microcontroller. The next step is 16-bit microcontrollers. Not necessarily, I would say. So I never learned how to program a 16-bit microcontroller. I jumped directly to 32-bit microcontroller, and that is quite possible. You do not need to know the knowledge of 16-bit microcontroller to program 32-bit microcontrollers, but again, it's a good skill to have. And 16-bit microcontrollers are not very common, but again, they are being used in different applications, and you can learn 16-bit microcontrollers if you want. So one common 16-bit microcontroller is MSP 430 by Texas Instruments. It's a most common 16-bit microcontroller in my opinion, and MSP 430 is a good architecture. You can learn it, and same way you program 8-bit microcontroller, you can program 16-bit microcontroller. Download the datasheet of the microcontroller you are using, and download the cross compiler, the toolchain. In this case, there is a Texas Instruments CCS or Code Compose Studio, which you can use to program 16-bit MSP 430 microcontrollers, and these are your IDEs which provide everything. Again, I think it's for Windows and Mac only, not for Linux. After the 8-bit microcontroller, you can go for 16-bit microcontroller, or directly you can skip to 32-bit microcontroller, which we will be talking about in a bit. So again, after 8-bit, you can go for 16-bit microcontroller if you have time and bandwidth, or like me, you can directly learn 32-bit microcontrollers. Alright, so by this time, you have knowledge of assembly programming language, C programming language, you have programmed Arduino, you have programmed 8-bit AVR or PIC microcontrollers, and maybe even 16-bit microcontroller. The next obvious step is to step up to 32-bit microcontrollers. And talking about 32-bit microcontrollers, the most common architecture available in the market, it's Advanced RISC Machine or ARM architecture. So ARM architecture is everywhere. In your phone, there is ARM architecture, the ARM Cortex-A series. So ARM architecture generally has 3 series, Cortex-A, which is meant for phones and everything which has an operating system. So your phone is using Android operating system, your ARM based notebooks are there which are using Linux operating system. So ARM Cortex-A series is meant for operating system based application. Then we have the ARM R series or ARM real-time series. So ARM R series controllers are generally used for real-time applications where very strict real timing is required, like anti-lock braking system, where you do not want any latency of any microseconds precision. There ARM R series are being used, and ARM R series generally supports RTOS or real-time operating system, and we will talk about them in a bit. The next in the list of ARM's Cortex series is ARM M series, and M series ARM are microcontroller series. So they do not support operating system like Linux or Android. They do not have real-time capabilities, but they are microcontrollers. They have good applications as you will. For example, the drone I'm using, the flight controller of this drone is based on ARM Cortex M series processor, and M series processor are generally microcontrollers. So you can program M series processor like you have programmed 8-bit or 16-bit microcontroller. So my personal recommendation is, after you have completed 8-bit and 16-bit, go for ARM Cortex M series microcontrollers initially and try to program them. So here I have one 32-bit ARM Cortex M4 series microcontroller by Texas Instruments. It is a TIVA C series based microcontroller, again based on ARM Cortex. But the most common ARM Cortex you will find in the market is by ST Microelectronics, also known as STM32. So the STM32 is based on ARM Cortex M architecture, and they are really very famous microcontrollers by ST Microelectronics and based on ARM M architecture. So as you level up, you will see there are M1, or M2 or M3 or M4 microprocessor in the same Cortex M series. So different features, more number of UART, more memory, and you will get new processor in the market of same core. So that is ARM Cortex M series. So you can program in the same way as you did for 8 or 16-bit architecture. You can use ARM GCC toolchain and different programs like Microvision Keel IDE, which is available to program these microcontrollers. And ARM Cortex M is again a really great microcontroller to learn and a good skill to have. So one thing I wanted to mention here is, while learning this advanced thing, don't forget the basics. And what I mean by basics is, like, consider this. So ARM is a RISC architecture, which is reduced instruction set computing. While learning the assembly, I mentioned 8051 and 8085, which is Intel based core. Those were CISC architecture, or complex instruction set computing. Also, all these architectures I mentioned is based on two principles of designing architectures, which is von Neumann and Harvard architecture. So again, I wanted to mention here is, while going ahead, do keep these things in mind, and do keep reading them, learning them, what they are, how it will impact your choice of microcontroller or microprocessor, like Big Indian or Little Indian, what it is, what it do. This may sound jargons to you. Again, feel free to stop this video, write these keywords and Google it out, and you will know what I'm talking about. And again, don't forget the basics. Your basics needs to be very strong and to the point before moving ahead. Alright, so by here we have covered assembly language, C programming, 8-bit microcontrollers, maybe 16-bit microcontrollers, and all about the basics things which we need to keep in mind. One thing here is, while learning advanced or advanced RISC machine, do focus more on architecture, because ARM architecture is very important, and ARM architecture has a lot of things to offer, and without the knowledge of architecture you cannot write good code, you cannot optimize your code. For example, if you compare ARM architecture and AVR architecture, let's talk about ADC, or analog to digital converter. So AVR architecture has a demultiplexer inside the ADC, so at the one time you can only use one channel or one sensor to convert its analog value to digital value. Whereas in ARM, let's say in LPC2148 ARM microcontroller, you can use multiple channels of ADC at a time. So these things you need to keep in mind while learning it. Keep a data sheet of the microcontroller you are learning handy, and you will find that learning the architecture is really helpful. You can optimize your code, you can use different things architecture has provided to ease your programming, and you can do different kind of things. For example, ARM architecture has inbuilt PLL, or phase lock loop, which you can use to have different clock frequencies inside. You can provide a different clock frequency to your AMBA bus, which is advanced multiplex bus architecture inside the ARM, and do different kinds of things like making your own USB controllers and whatnot. So what I'm trying to say here is, focus on architecture, focus more on what the manufacturer has provided to you, and write code according to you, and not just write code. Read the data sheet and see what different architectures are provided. Specifically in ARM, there are different modes, like thumb mode, where you can execute a 32-bit instruction in 8 or 16-bit format. There is Jazzle mode, where you can execute the Java bytecode directly, and different kind of things are available. For example, shadow registers are available, so you can do digital signal processing as well. So focus on architecture more, and you will learn different things, and you will learn optimizing your code more efficiently. So once you have good understanding of programming 32-bit ARM microcontrollers, now it's time to level up your skills, and from here you can move to real-time operating systems, or you can move to porting Android or Linux to your processors, and choose different processor from here. And both of these skills are really important to any embedded software engineer. You will see that some places you will be programming real-time operating system, which is also short known as RTOS, and somewhere you will need a full-fledged operating system like Linux to do what you are trying to do with your embedded product. I would highly recommend you to learn both of these, and give separate time slots to each of them, and spend some good amount of months to learn both of them and implement them practically to some of your projects. And you will see that you will be getting good skills, and by the time you graduate, you will have everything required to make a career in this domain. So on this note, let's talk about a little bit about real-time operating system and what is RTOS. So RTOS is basically a small operating system which runs on your microcontroller or microprocessor, which will give it real-time features like, for example, you want a very real-time constrained application like anti-lock braking system. When you brake the car, you want the tires not to be locked, so you need an actuator to be doing back and forth inside the tire, and this needs to be very real time. There should be no delay. That is where RTOS comes into picture. So it's a small operating system which runs inside your controller, and it do memory management, time management for you. So you just need to write the application, and you do not need to worry about what's happening underneath, how it's doing memory management, how it's doing resource allocation. So you do not need to worry about this, and RTOS will handle everything for you. So what you can do is take an open source RTOS and port it to your microcontroller and then program it. For example, there are different RTOS available in community. Very common one is free RTOS. Then there is also Zephyr RTOS by Linux Foundation, and you will see there are different RTOS available. Just Google RTOS and you will see different RTOS popping up. So you can port this RTOS to your processor. Here you might also need to buy a different reference target based on Cortex R or Cortex A architecture, and do invest into that. Don't worry, it's really a good skill to have. And RTOS are generally programmed again in C. You need to have system calls, you need to learn how socket programming works, maybe how IPCs or inter-process communication work, how interrupts work, how you handle the interrupts, and different kind of things you will be learned while you were exploring an RTOS, and again a really good skill to have whatsoever. So do learn RTOS, spend some months learning this and make some projects out of it. So free RTOS is there, Zephyr OS is there, and you can Google different RTOS. So now you are familiar with assembly C, all kinds of different word sizes, microcontroller, also RTOS. The next and I guess the most important step is to enter the world of operating system. Most common operating system used in embedded system is of course Linux, because it's an open source operating system. It's heavily supported by community, it's supported on different architectures. So Linux is a good skill to have, and all the software which I named previously like Microvision Keel or CodeCompose Studio are either for Windows or Mac OS 10. That's why you need to keep Windows at this point to use those IDEs. But if you are someone like me who are into professionally embedded system domain, then let me tell you, you do not need to have Windows. You can do everything on Linux, but you need to have good exposure of command line. So here I would recommend to install Linux as your operating system. Maybe initially you can do it on a virtual machine or have a dual boot system. Installing Linux on a system will open the doors for different kinds of things, and ultimately you would be using Linux in your industries as well if you are doing these kinds of things. So don't hesitate installing Linux. I recommend installing latest Ubuntu supported version on your workstation, and from here you can use Linux for everything. So now let's talk about Linux and your microprocessors or microcontrollers. So Linux is an operating system and it's an open source operating system. It supports different architectures. It supports ARM architecture. So ARM A series, Cortex A series is entirely meant for operating system like Linux and Android. You can use Linux kernel and Android kernel and port them to the ARM architecture. And once operating system like Linux takes over your processor, then you need not to worry about memory management. You need not to worry about writing data to registers. You need not to worry about RAM management, interrupts handling. Everything will be done by the kernel itself. So kernel is a part of operating system which will manage everything from your memory, from IOs, from resources, and everything you will do with the help of kernel, and by requesting kernel different resources using system calls, using IOCTL, if I may, and different file systems which are made available to do different kinds of things for your embedded product. Having a Linux on your processor is having a small computer in itself. It will boot, it will have a kernel, it will have a root file system. It will also have something called DTB or device tree blob, which we will discuss in some later videos maybe. And these things are supported on single board computer, like most common one which I can tell is Raspberry Pi. So this Raspberry Pi, it is having an ARM Cortex A series microprocessor, and it is running a full-fledged operating system. In this case, it can run Raspbian, it can run Ubuntu, it can run Mate, which are different Linux flavors. So I'm talking about these kinds of things, having single board computers and installing Linux on their SoCs and doing different things. So as you can see, Linux are supported on different architectures. I can share this Onion Omega based board which also runs on Linux. It runs on LEDE or OpenWRT based Linux. It also runs on Intel based architecture, which is x86 architecture. So I am holding a Intel Edison single boot computer. It also runs on Linux. It's a different architecture but same operating system. So you see ARM architecture and x86 architecture both support Linux in this case. So from this small board to this full big board, Intel Galileo, you also run Linux, and some also big boards like this Atmel based smart board meant for some industrial application. Everything runs Linux. So once Linux is installed, it will boot as your system, and you can do different kinds of things. And when you install Linux on your single board computer for the purpose of learning, for the purpose of becoming an embedded software engineer in future, then what things you need to learn are different keywords I'm again throwing at you, like bootloader. So bootloader is something which allows an operating system to boot on your system, and most common bootloader is U-boot. You need to learn DTB or device tree blob. Device tree blob tells the kernel the connection of SOC, like which pin is connected to LED, which pin is connected to UART, and different kinds of thing. You need to learn kernel. You need to have the knowledge of file systems. So file system are where you keep your files, and different kinds of things you can do by writing the data into the file or by reading from the file. Then you can learn about device drivers, what they are, when a device driver is being probed and used, and how you can attach external devices, and you can program device driver for your external device. Also, once you have the operating system, then you can program directly onto that board. For example, you can program Raspberry Pi in Python, you can program it Node.js, you can program it C, C++. Because it's an operating system, consider it as your laptop, and you can program it any language possible. So that's a very good thing. And what I recommend you here is learn in depth of system C programming, like multi-threading, like IPCs, interrupt handling, and all kind of things you will learn, and you will become a better embedded software programmer. So these are all the different skills which you need to acquire to be an embedded software engineer. And this might sound very intimidating, but don't worry, you do not have to do this in 15 days. Take your time. So I started during the first year, and I take like 4 to 5 years to acquire these skills, and that is the time frame which you would be looking to if you wanted to be a serious embedded software engineer in future. So take your time, don't rush. And in the last, I would be sharing a couple of different skills which are good to have, but not necessary to have to be an embedded engineer. And these are something like VLSI. So VLSI stands for very large scale integration. It's basically for chip designing. So chip designing are done again in C programming language, and specifically hardware descriptive language, which are made to program chips. And I would recommend you to learn either VHDL or Verilog HDL. HDL stands for hardware descriptive language. So knowing this language will give you a small edge over others, and it's a good skill to learn again. Not necessary, but again, if you learn, you will definitely have some more skills in your resume. With VHDL and Verilog HDL, you can program your own chip, and it's a trend to have a built-in FPGA and CPLD on a microprocessor. So you can write code for your microprocessor, and then you can modify the hardware built in and do different kinds of things. So FPGA is a field programmable gate array, and CPLD is complex programmable logic device. Consider this as like thousands of gates inside a chip waiting to be programmed to do some function. So these are things which you can program with VHDL. Other things which are really desirable is debugging. So using a JTAG debugger. JTAG stands for Joint Test Action Group. JTAG usually help you to have breakpoints inside your program and debug your firmware or embedded program. It is a 10-pin connector which you can use and debug your program on the computer. Schematic and PCB designing, again not a must, but a good skill to have. IoT or Internet of Things, and what I mean by IoT is communicating your embedded device to clouds, and this again is a very big field, and maybe I will make a video on this in future. So basically you can connect your embedded devices to the internet using Ethernet, LAN, Bluetooth, and gateways and whatnot. So learning how to communicate to the cloud by different protocols like MQTT or CoAP and LWM2M. So these all kind of things comes under IoT, which you can do. Alright, so that is all for today's video. Hope you enjoyed it and get some insights on how you can become an embedded software engineer. Share it with your friends who are looking to make career in this domain, and comment it down below if you wanted to see more of such videos and maybe some different domains. I can bring some more people on this channel. They can talk about their domains. So thank you very much. That's all, and I'll see you in the next one.